Hello, everybody. So this is part of Unit 7 on chemical reactions. Today we're going to learn how to balance chemical reactions. So learning how to balance chemical reactions is very straightforward. There's a little bit of math involved. So let's get right to it. I'm going to turn off my image just so that we have a little bit more room. There we go. Okay, so here we have some chemical reactions. We have on the left of the arrow, we have the reactants. And then on the right of the arrow, we have the products. So think of this as two moments in time. What the arrow represents is the process of moving from the reactants to the products. So reactants is before and products is after. Okay, so the technique is to make a table. I'm going to put an R to represent the reactants, and then I'm going to put a P to represent the products. And then I'm going to list all of the atoms that are in this chemical reaction. We have aluminum, we have hydrogen, and we have chlorine. The next step is to count the atoms. On the reactant side, we have one aluminum, we have one hydrogen, we have one chlorine. On the product side, notice that we have one aluminum, we have three chlorines, and we have two hydrogens. So the problem here is that, for example, in the case of chlorine, you start out with one atom of chlorine, and then you end up with three. Now that's not allowed according to conservation of mass. You cannot create or destroy atoms. Atoms, it turns out, are very robust particles. It takes very high temperatures or pressures in order to cause them to change. They don't just disappear in general. Okay, so now we're going to do a little bit of math. And notice that the aluminums are okay. The hydrogens, you start with one, you end up with two. The chlorines, you start with one, you end up with three. So you have to make a decision. What are you going to balance first? Well, I am going to balance the chlorines first instead of the hydrogens. And the reason I'm going to do that is that this hydrogen on the product side is just by itself. So whatever way we change this, it's not going to affect any other type of atom. So there's one chlorine on the left, there's three on the right. So I'm going to put a 3 here on the left, on the reactant side. What that does is it changes the hydrogens to 3, and it changes the chlorines to 3. Okay, and that brings up a point. Notice that the only thing I'm doing is I'm changing the coefficients, and these are the numbers in front of the formula for the compound or the molecule that we're dealing with. You're not allowed to change subscripts, only coefficients. Okay, so the chlorines are balanced, but now the hydrogens are not balanced. In order to balance the hydrogens, we have to think of a common multiple, the lowest common multiple between 3 and 2, because there's 2 hydrogens on the right and there's 3 on the left. So what's the lowest common multiple? Well, what is 3 times 2? It's 6. So 2 times what number equals 6? A 3. I'll put a 3 here, and that changes the number of hydrogens on the right to a 6. And then on the left, instead of a 3 in front of this HCl, I need a 6. So I'm going to erase that 3. Erase the 3. and I need to put a 6 there. So that's going to make the number of hydrogens 6. It's also going to make the number of chlorines 6. Okay, so the hydrogens are now balanced. So the chlorines have 6 on the left, and there's 3 on the right. So what times 3 equals 6? A 2. So I'll put a 2 there. And that changes the number of chlorines on the right to a 6, but it also changes the aluminum to a 2. Okay, so on the left, there's 1 aluminum. How do I make 2 aluminums? Now, please notice, you are not allowed to do this. If I put a little 2 there, that's 2 aluminums, right? That makes 2 aluminums, but that is illegal. You're not allowed to change subscripts. You're only allowed to change the coefficients. So I'm going to go back to my pen and I'm going to put a 2 there. Now it's legal. Please notice in this example, I balanced the chlorines first, but I had to go back. I had to backtrack. So that's the way this goes generally, is if you have several atoms you're trying to balance, sometimes you'll balance one and then find out that it's a blind alley and you have to back out and start over again. That's very common with this method. Okay, let's try the next one. Again, we have our reactants and we have our products. In this reaction, we have As, which is arsenic, and we have chlorine. On the left, we have 1 arsenic and we have 2 chlorine. On the right, we have 1 arsenic and we have 5 chlorine. 5 chlorine, well, see this little 5 here? This little 5 right there. That means that whatever is directly to the left of the subscript, that's how many atoms there are. This 5, notice it does not affect the number of arsenic atoms. It's only the atom that it's attached to, that the subscript is attached to. Okay, so obviously in this case, I'm going to balance the chlorine first. What is the common multiple between 2 and 5? What's 2 times 5? That's the lowest common multiple is 10. So 5 times what equals 10? A 2. I changed the coefficient to a 2, and that makes that 5 a 10. It also makes this 1 a 2 for the arsenic. 2 times what equals 10? 5. So this 2 becomes a 5. Okay, so what do I have to change on the reactant side for the arsenic to have 2? Well, I put a 2 here. 2. And you're done. What this says is that it takes 2 arsenic atoms and 5 chlorine molecules to make 2 formula units of arsenic chloride. And by the way, this is called rat poison. And rat poison, I'm not sure what it does. I think when the rats eat it, it causes it's something about the blood. But the thing about it is that it's tasteless. So you can sprinkle it on rat bait and they will eat it and they won't know that they're eating poison. Okay, what about the next one? We have phosphorus, a phosphorus molecule, tetraphosphorus or phosphide, and then you have hydrogen gas, and you can make phosphine. Okay, so reactants, products. We have phosphorus and we have hydrogen. 4 phosphorus on the left, 2 hydrogen on the left, 1 phosphorus on the right, 3 hydrogen on the right. So typically I like to balance the hydrogens first. So what's the common multiple between 2 and 3? the lowest common multiple is 2 times 3, which is 6. So 3 times what equals 6? A 2. Okay, so that changes that 3 to a 6. That changes this 1 to a 2. On the left-hand side, 2 times what equals 6? Well, a 3. So I'm going to change this 2 to a 6. So the hydrogens are balanced. Now, how do we balance the phosphorus? Well, there's 2 on the left and 4 on the right. So what times 4 equals 2? Well, why don't we just divide it by 2? So I'm going to put a 1/2 right here. 1/2 times 4 equals 2. And I have no problems using fractions when I'm doing this. Now, obviously, you can't take a phosphorus molecule and divide it by 2 because this P4, if you divide it by 2, it's like cutting it in half. You no longer have P4, you have P2. But please be aware, we're not dealing with individual molecules when we're doing these reactions. We're dealing with trillions upon trillions upon trillions of these particles in a very tiny drop because these particles are so small. But when I say 1/2, I'm meaning the proportion. 1/2 parts of the P4 plus 3 parts hydrogen gas will make 2 parts phosphine. And by the way, phosphine is a fumigant, right? It's a very toxic gas. I'll put a little G here to indicate that it's a gas. It's a very toxic gas that can be used to fumigate whatever you need to fumigate. Like if you have a roach problem in your house, you could put a big, huge balloon over your house and fumigate the house, and it'll kill whatever insects are inside. Okay, let's try the next one. Reactants, products. We have Au, which is gold. We have S, which is sulfur. We have H, which is hydrogen. And I need to clean that up a little bit. Okay. H. Okay. On the left-hand side, on the reactant side, we have 2 golds, we have 3 sulfurs, and we have 2 hydrogens. On the product side, we have 2 hydrogens, we have 1 sulfur, and we have 1 gold. Okay, so again, this gold on the product side is just sitting there by itself. So whatever coefficient we put on there is not going to affect any other atoms. So because of that, I'm going to balance the sulfur first. So we got 3 sulfur on the reactant side. We got 1 sulfur on the product side. So to fix that, I need to put a 3 in front of the hydrogen sulfide. And that changes the number of sulfur on the product side to a 3. But it also changes the number of hydrogens on the product side. What is 3 times 2? It's 6. So I have to change that to 6. Okay. So we have 6 hydrogens on the left of the arrow. We have only 2 on the right. So what times 2 equals 6? A 3. I'll put a 3 here, and that makes that into a 6. Okay, finally, we have 2 gold on the left. We need 2 on the right, so I'll put a 2 there. And that changes the 1 to a 2. Okay, so this gold sulfide, that's actually, let's just say that that's in water, AQ. What that means, the AQ, is that it's dissolved in aqueous solution, which is water. So this gold sulfide, you might go to a gold mine. If you own a gold mine, you might have all of this water that has dissolved gold in it. And you want to get the gold out so you can sell it for profit. So what you can do is you can take this pool, this waste pool of water that contains some gold, and you can bubble hydrogen gas through it. So this would be a gas, hydrogen gas. And what that'll do, it'll produce hydrogen sulfide, which is very stinky, very smelly. But it also causes the gold to fall out as a solid. Okay, so here is a chemical equation that is very useful to people that own a gold mine. Okay, for the next one, we have what's called a combustion reaction. So here we're taking a hydrogen, carbon-hydrogen compound, hydrocarbon, and we're burning it with oxygen to produce carbon dioxide and water. And this particular hydrocarbon is sugar. So this is the chemical formula for sugar, and in particular glucose. So this is what is going on inside the cells of our body, and this is how we get a lot of energy. So another product of this is energy. Okay, so same procedure. We have our reactants and we have our products. We have carbon, hydrogen, and oxygen. On the left, we have 6 carbons, we have 8 hydrogens, and we have, this is kind of tricky because we have oxygen in 2 different molecules. We have 6 in the sugar plus the 2 in the oxygen molecule. 6 plus 2 equals 8. Okay, on the right, we have 1 carbon, we have 2 hydrogens, and again, we have 2 in the carbon dioxide and 1 in the water. That's 3. Okay, none of the atoms are balanced, so where do I start? It's my suggestion that we start with the hydrogens first, and then we'll do the carbons, and then we save the oxygens for last. I like to do that because this oxygen here on the product, a reactant side, it's there by itself. So if we change everything, and then we can just balance the oxygens by just putting whatever coefficient we want. It's not going to affect any other atom. Okay, so let's do the hydrogens first. I always like to start with the hydrogens in combustion reactions. Okay, we got 8 hydrogens on the left. We got 2 on the right. What times 2 equals 8? 4. So 4 times 2 equals 8. That'll change this 2 to an 8 on the product side for the hydrogens. Okay, what about the carbons? We got 6 on the left. We got 1 on the right. So I'm going to put a 6 on the product side in front of the carbon dioxide, and that'll change the carbons to 6 on the right. How many oxygens do we have on the right now? We have 6 times 2 equals 12 from the 6 carbon dioxides. And then we have 4 times 1 equals 4. 12 plus 4 equals 16. So instead of 3, we now have 16 oxygens. Okay, now we're ready to balance the oxygens. On the reactant side, we have 8, but we want 16. So what times 8 equals what times 2 equals 16? Well, that's not right? So we have the 6 from the sugar. We have the 2 from the oxygen. So we already have 6. So really, we only need 10 more. 6 plus what equals 10? 6 plus what equals 16? 10. So 2 times what equals 10? I'm going to put a 5 here. Okay, let's see if that worked. 5 times 2 equals 10 plus 6 equals 8. equals 16. And that worked. Okay, and then the final one, again, we got reactants and we got products. We have sodium, we have silicon, and we have fluorine. Okay, sodium, we have 2 in this sodium silicon fluoride particle formula compound, and then we have 1 sodium here, so that's 3 sodiums. Silicon, we have 1 on the reactant side, and fluorine, we have 6. The product side, we have 1 silicon, 1 sodium, 1 silicon, and 1 fluorine. So what are you going to balance first? Well, why don't we balance the fluorine first, since it's in on both sides. If we balance fluorine, we're also going to have to balance, it's also going to affect the sodium. So I'm going to put a 6 in front of the sodium fluoride on the right, and that'll give us 6 fluorines. And it will also give us 6 sodiums. Okay, so the fluorine's balanced, but the sodium is not. We have 3 on the left. We want 6 on the reactant side. Okay, we've already got 2, right, in the sodium silicon fluoride. We need 4 more. We want 6. We already have 2. No, we already have 3. We need 3 more. Okay, so 6 minus 2 is 4. So why don't I put a 4 here? So that would be 2 plus 4. Instead of 3 now, I have 6. Did that work? Yeah, that worked. It's balanced. Okay, just to wrap things up, let's discuss a couple of questions. Why does a chemical equation have to be balanced in order to be correct? And maybe I'll get my highlighter. There we go. Okay, conservation of mass, right? Conservation of mass is whatever you start out with, you have to end up with. And in the case of atoms, because atoms are so indestructible, whatever atoms you start out with, you better end up with under normal conditions. Of course, you can have a nuclear reaction and you can split the atom and make new types of atoms, but under normal conditions of everyday life, that does not happen unless you're inside a nuclear bomb or a nuclear reactor, or you're inside the sun. So the number and type of atoms that you start with must equal the number and type that you end up with. What does a balanced equation tell you about the reaction? Well, basically, the balanced chemical reaction gives you the recipe. For example, let me go back to my pen. Okay, so here's how we make water. We take hydrogen gas, and we take oxygen gas, and we can make water. And if we cool it down enough, we can actually make liquid water. Put a little L there. But you'll notice in this chemical reaction, we have 2 atoms of hydrogen on the left, but on the right in the water molecule, we only have 1. So to fix that, I'm going to put a 2 here. Now 2 oxygen atoms on the left, 2 oxygen atoms on the right. But that also changed the number of hydrogens. 2 times 2 is 4. So I have to put a 2 here to have 4 hydrogens on the left. So what this tells you is that in order to make 2 parts or 2 molecules or 2 parts of water, you're going to need 2 parts of hydrogen gas and 1 part of oxygen gas. And really, that's how we need to think about this, not in terms of molecules, or we need to think of it in terms of ratios. So the recipe, it tells you what you need, the ingredients, in this case, hydrogen and oxygen, to get what you want, in this case, water. And it tells you how much hydrogen or oxygen you need to make how much water. So it tells you what we call the proportions. So that's it for this video, and I will see you in the next video. Bye-bye.